Hi. All right. So what we're going to cover today is Thevenin's theorem. Okay. What's Thevenin's theorem? Who is Thevenin? Let's answer these questions. Okay. Thevenin has a theorem. Now, Thevenin is actually a French telegraph worker. So you got to imagine, it wasn't that long ago. We're talking, let's see, we're in 2020 right now. So you're looking at about 130 years ago that the most advanced usage of electronics was tapping two wires together to send dits and dashes and transmit messages over, two wires over great distances. That was the extent of our electronics. Leon, and like I said, he was a French telegraph worker. So hopefully, is anyone in this class French? Because I'm gonna butcher his name. Leon Charles Thevenin. Okay, so French telegraph worker from about 1857 to 1926. So, I mean, as far as the human experience is concerned, this is really not that long ago, considering how long we've kind of been on this planet for. And now we have really cool devices in our pocket that can do all sorts of computation and connect to a global internet, and you can shop and you can FaceTime and you can do all sorts of things from your smartphones. So fairly impressive to come this distance in such a short amount of time. I think that's always mind-blowing to me. And he was very interested in Ohm's law and Kirchhoff's current law, as you probably would be if you were a French telegraph worker during this time period. And just to put things in perspective, Ohm's law comes from George Ohm, and he was around 1789 to 1854. Okay, so, not that far before Thevenin. And Gustav Kirchhoff, responsible for all of those useful rules, Kirchhoff's voltage law and Kirchhoff's current law. Was 1824 to 1887. Okay, so everything that we've been really talking about is really kind of a recent innovation. Okay, and what exactly is Thevenin's theorem? Well, Thevenin's theorem states that any linear two-terminal, and by two-terminal, I just mean that there are two connection points in a circuit. So any two-terminal network. Now, network of resistances and sources can be simplified by an equivalent circuit consisting of a single voltage source we will call this single voltage source VTH for the Thevenin voltage, and a single series resistance. Which we will call RTH for the Thevenin resistance. Okay, so what are we saying here? Any linear two-terminal network. So all the circuits we've looked at thus far, all the circuits we've worked with, they're all linear. And two terminals, so we're going to have 2 points of that circuit. So let's just say we have this black box circuit over here. Doesn't matter what's in it as long as it has sources and resistances. But we are looking at this circuit from the perspective of any 2 points. So for all the circuits we've seen thus far, you can just put a terminal point at and call it A at any point along that circuit. And I can pick another point and call that B from any point of that circuit. So any of the circuits that we've seen thus far, just put an A and a B anywhere on that. And if we do that, we can go ahead and derive an equivalent circuit that behaves in every which way, shape, and form to the more complicated circuit, which consists of a single voltage source, VTH, with a series resistance, RTH. Okay, so Thevenin voltage and Thevenin resistance. And it'll behave identically to this circuit from the perspective of these 2 terminal points. So basically anything that I connect between these, between A and B in our Thevenin equivalent circuit, will behave identically to that same thing connected between A and B. So if I were to take a resistor and plug it into between A and B over here, I would get a current and a voltage through it. And if I took that resistor and I plugged it over to this circuit, I would get the same voltage and current through it, as long as it's the same resistor. So these 2 circuits will behave identically, okay? So let's go ahead and say this is our original circuit, and it doesn't matter what's in here. I could have 100 voltage sources and 2 resistors. I could have a zillion resistors and 5 voltage sources, and I could configure it however I wanted, but I bring it out to these 2 terminals from 2 wires, 2 junctions, 2 nodes in my circuit, and I can derive this, which only consists of 1 voltage and 1 resistor. So it's actually a fairly useful reduction. Okay, now the result that we get from this process of taking a circuit and deriving a Thevenin equivalent circuit from it, the result is referred to as the Thevenin equivalent circuit. Let me change colors here because everything's all monochrome right now. Thevenin equivalent circuit. Okay, and the process of converting this into this, we will refer to as Thevenizing the circuit. At least that's what people generally say. You Thevenize the circuit and you get the result of a Thevenin equivalent circuit, okay? And then the result is always 1 voltage source with 1 resistor in parallel and our 2 terminal points, and we will get a circuit that behaves every which way and is fundamentally identical in performance and everything to our original circuit, regardless of how much stuff is on there. Somebody asked, what is Morse code? So Morse code is how we used to send messages back in the days of the telegraph. So I made a reference to Thevenin being a French telegraph worker. So I got to do this because, you know, if there's a question about what's Morse code, I can't let that go for too long. Let's go ahead and drop this for a second and let me pull up a new and Morse code. Morse code. Aha. So basically, international Morse. Oh, this image is not looking good. Can I do that? Yes, I can. Okay, so international Morse code. Every letter is assigned a combination or a sequence of dots and dashes. So this is quite literally, if I was going to send a message and I wanted to say A, I would tap on the switch and I would say dit, and then do a long one, a dash. Dits and dashes. That's what these dots and dashes are referred to as. So when you wanted to spell out a word, it took quite a while, right? And let me go ahead. And we do have a little bit of time today. Dit, dash, 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 dit. So what, SOS? Is there a trick to remember it? Actually no. Well, there are different ways and approaches to learning Morse code. And actually, you don't want to sit there and learn it very slowly. You want to sit there and learn it at full speed. That's the best way to learn Morse code, because your mind will actually learn the letters and the sequence without having to do this little intermediary processing where I got to convert dits and dashes to the letter and then assemble the letters. You actually want your brain to be able to process the sequence and instantly turn it into the letter, as opposed, so it's like learning a language as opposed to learning a conversion. So there was a lot of work done in this. If you think about military times and Navy back in World War II and World War I, and even to this day, the crazy thing about Morse code is because how simple it is very easy to get messages long distances, because if you think about the noise and the signal strength, you don't need much signal strength, and you can take a lot of noise in your signal and still extract a meaningful message from it when you're using something like Morse code. And let me go ahead and pull up my favorite video of somebody doing Morse code. Yes, I have. So I'm actually a ham operator and I have a ham license. Ham radio is kind of an old kind of a hobby of making antennas and making radio receivers and sending messages, you know, across the world. You can actually get a message over to Europe or Australia. And so I got my license back in like 2003. There are different licenses involved with it that give you access to certain frequencies that you can transmit on. There's actually just a test that you take, and I will say the technician license, which is the first license you would get, is very easy to get, especially after taking this class. There's a lot of basic questions about like Ohm's law and power, and you know, the exam is designed for people who are not computer/electrical engineers, and so the exam is actually pretty straightforward. You can probably score 100 on it with like a couple hours of practice. But let me go ahead and pull up this video of Morse code. Okay, so I find this kind of amazing, and I know this is completely off topic, but like, dude, check out this guy. He's just like reading the paper and having a conversation with a friend. He's not even thinking about Morse code. He's just thinking about what he wants to say, and the dits and dashes are just being sent out. And so that's kind of the key that you would use to send Morse code. And so transmitting Morse code via radio was an incredibly powerful way to send messages my favorite, I think my favorite comment down here, where everybody gangsta till your grandpa starts to speak Morse code. Okay, so that's a fun little side conversation about something that's kind of relative. So now at least you can kind of put it into perspective about, you know, what Thevenin was kind of doing at the time and the technology he was working with. Okay, so let's get back to this Thevenin equivalent circuit idea. Okay, so just by looking at what our reduction is going to result with our Thevenin equivalent circuit, all we have to do is find two values from our original circuit. So we just need to derive VTH and derive RTH. And if we find those two values, we just plug it into this circuit and we have a Thevenin equivalent circuit, okay? So all we have to do is find VTH and find RTH. So now there's going to be a process for finding each one of these values. Once you have two of them, you just plug them in. So let's go ahead and let's describe how we get VTH and how we get RTH. Okay, so VTH, what's VTH? VTH is going to be the open terminal voltage felt across the load terminals A and B. That's all it is, okay? All we have to do is find the voltage between A and B. If we find the voltage between A and B, we have VTH. It's that easy. It's that straightforward. So let me go ahead and let me put, before we get to RTH, let's go ahead and kind of show how we get VTH. I'm going to put up a couple of circuits here. Let's do one here. Let's do another one. And let's do a third one. Okay, now these circuits as they are right now, could we do a Thevenin equivalent circuit? Can we derive one from these? No, because we need to have those two load terminals. So on your problem that you start with, you're gonna need to have a starting point. I wouldn't say a starting point, but you're gonna have to find 2 points from which you will derive your Thevenin equivalent circuit from. Across. So the reason the word load is in here is because we think about attaching something to A and B. And anytime you're going to be attaching something like that, load. Okay, so load terminal, this is just our 2 points that we're going to connect something to eventually, okay? But it's not, we don't connect anything there for the sake of deriving our Thevenin equivalent circuit. Okay, so let's go ahead and let's just say 10 volts and 10 ohms. All right, tell me, what's the voltage that we would find between points A and B in this circuit?
10 volt.
Yeah, 10 volts, right? So what's VTH? 10 volts. So you just figure out what the voltage is between these 2 points. Let's go ahead and let's put A and B. Let's switch this problem. Let's do 100 ohms over here and 400 ohms over here. And let's do 5 volts. And let's put our load terminals here and here. Okay, so from this problem, can we figure out what VTH is? Absolutely. So we have 5 volts divided by a total resistance of 500 ohms. That's going to give us our total current, right? So just like we solved the circuit before, we're just solving it with a goal. Our goal is to find the voltage between A and B. So if I take 5 volts divided by our total resistance, 500 ohms, gives us 10 milliamps, right? So we have 10 milliamps here. And so we have our voltage drop across our first resistor, our voltage drop across our second resistor. So let's do 0.010, that's 10 milliamps times 100 ohms. I'm just applying Ohm's law here, and we get 1 volt across this, right? So we have 1 volt across our first resistor, and our second resistor would have 4 volts across it. So what is VTH in this problem? What's my voltage between points A and B? Yeah, 1 volt. Okay, so what about if I took this same circuit and now switched it up? I'm going to take the same exact circuit. Let's do 5 volts, 100, 400, and we know we have 1 volt across the first one and 4 volts across the second one. See what I did here? I just moved my terminals. I put it to a different point. Even though it's the same circuit, I put my points across the 400 ohm resistor as opposed to anywhere else in the circuit. So then the question is, what's VTH now? Well, it's 4 volts, right? Okay, so I get a different, even for the same circuit, I get a different Thevenin equivalent circuit depending on where my load terminals are, right? So when you're solving for a Thevenin equivalent circuit, when you're performing that Thevenizing process, it very much depends on where A and B is. Okay, so the same circuit, if A and B is in a different spot, you're going to get a different output. Okay, so that's how we get the Thevenin voltage. You just find what the voltage is between points A and B and call that your Thevenin voltage. I'll go ahead and skip this last one for now. We'll do something. We'll do a problem similar to that once we learn the next 50% of the puzzle, which we need to figure out how to find the Thevenin resistance. Okay, so Thevenin voltage, easy to find. Okay, Thevenin resistance, also easy to find. Okay, RTH, what is RTH? Well, RTH is going to be the resistance seen when looking back into the circuit from the 2 terminals with our voltage sources shorted. Okay. So a little high level here. The resistance seen when looking back into the circuit from the 2 terminals with voltage sources shorted. We're disabling these voltage sources. Okay, very similar. The same thing that we did when we wanted to use superposition and we wanted to disable a voltage source. We just short from one side to the other. Okay, let's go back to our problem over here. Okay, let's go ahead. Let's look at this one first, because this one's going to make more sense. Now, even though we already solved this for VTH, don't reuse the same problem. We solved this for the voltage. Now we're going to go ahead and find the resistance. It's essentially a new version of this circuit. So what did we say? We need to disable our voltage sources. So we're going to go ahead and short our voltage source. And we had 100 ohms and we had 400 ohms. Okay? So, what do? Well, we short out our voltage sources and we find the resistance from the perspective of A and B. Okay? So, we're solving for the resistance just like we did in that second lab, right, where we had an A and a B and you found the resistance between those 2 points. We're doing the same thing here. So over here, look at how I can redraw this circuit. This 400 ohms, is it in parallel or is it in series with this 100 ohms? If you're ever in doubt, pretend that there is current flowing from A to B and use that to help you out. If I redraw it, though, I think it's going to be very clear. Our 100 is just in parallel with the 400 ohm, right? If you pretend that there is current going from A to B, it enters this dividing node. Some goes here, some goes here, and then it sums back together at this summing node. Well, your dividing node and your summing node define your 2 points of parallelism, right? So this 100 ohm is in parallel with 400 ohms, and all we have to do to figure out what RTH is in this problem, RTH equals 400 times 100 divided by 400 plus 100, right? So what does that end up being? 400 times 100 divided by 500, 80 ohms. Okay, so that's how you find RTH. You just go ahead, short out all your voltage sources, and then solve for the resistance between A and B. Everyone good with that?
Yeah.
Cool. Let's go. Let's look at this one. If I short out my voltage source, what's my resistance between A and B?
0.
Yeah, it's 0, right? That's why I didn't do this one first, because when you short out that voltage source, you are also shorting out this resistor over here. Okay, that's why I didn't do that one first. Okay, so that's how we find RTH. That's how we find VTH. Let's go ahead and let's do a problem. Let's do a little more elaborate of an example. let's do 100 volts, 25 ohms, 100 ohms, 25 ohms down here, 100 ohms over here, and we have A and B. Okay, and let's keep our eye on the prize. What do we want to do? We want to Thevenize this circuit. Or in other words, derive a Thevenin equivalent circuit. Okay, what's that going to look like? Well, it's going to look like a single voltage source with a value of VTH applied to a series resistance with a value of RTH, and we just need to find these two. And once I Thevenize, or I derive a Thevenin equivalent circuit for my original circuit, I will have a circuit that behaves identically to this circuit from the perspective of points A and B, meaning whatever I attach to this circuit would behave the same way as if I attached it to this circuit. There would be no difference between the two. Okay, so let's go ahead and let's solve. Let's find this. All right, what's our first step? What are we going to try and find first? Let's try to find VTH first. Okay, so I'm going to keep this page clean. I'm going to redraw with the goal of finding VTH. Okay, we have 25, 25, 100, 100, and 100 volts. And we have our points A and B. Okay, what do we do to find VTH? You just solve for the voltage between points A and B. Okay, how do we do that in this problem? Well, let's just use all of our basic rules and techniques that we know thus far in order to do this. I have 100 volts applied to all of these resistors. I just need to find the voltage between A and B. So, not a bad idea to start with our total resistance. What's our total resistance? Well, at this point, I feel like I can go ahead and skip a few steps, but I have 100 in parallel with 100. That's 50. This whole thing reduces to 50. I have 50 in series with 25 and 25. So I have 100 ohms total, correct? So that means I have 100 volts applied to 100 ohms. I get 1 amp, right? So RT is 100 ohms. We have 100 volts applied to it. So my current going through all this is 1 amp. Everyone good with that? Okay, let's take our total current, backfill this into our original circuit. I have 1 amp here. I have 1 amp over here. Okay, so my total current is leaving the source. It must be coming back to the source. What's my voltage drop across that first 25 ohm resistor? We'll just apply Ohm's law. 1 amp times 25 ohms gives us 25 volts. What about down here? Same thing. 1 amp going through a 25 ohm resistor gives us 25 volts across the 25 ohm resistor. Okay, now let's look at KVL. I start at 100. I lose 25 volts. Therefore, I must be at 75 volts. Okay? And over here, I end at 0 volts, and I dropped 25 volts to get to 0 volts. I must have been at 25 volts. Now check this out. What's my voltage drop across this 100 ohms? It's just 50. It's the difference between my voltage at both of these points. I'm at 75 on this side. I'm at 25 on this side. I have 50 volts across this resistor. I'll do this in blue to stay consistent with what I've been writing thus far. Okay. This 100 ohm is in parallel with this 100 ohm, or I can look at the wire and look at the voltage. I have 75 volts here. I have 75 volts here. This wire, I have 25 volts at every point along this wire. What's my voltage drop across that 100 ohms? It is 50. Okay, again, I got to find the voltage between points A and B. Well, A is directly connected along this wire with 75 volts. B is directly connected on this wire with 25 volts on it. So my voltage between points A and B has to be 50 volts. And that makes sense. My A and B is, well, it's in parallel with my 100 ohm resistor, which is in parallel with this 100 ohm resistor. So I should have 50 volts across all of these. So VTH is 50 volts. Everyone good with that? How we got 50 volts? Sweet. So let's go ahead. What's VTH equal to? 50 volts. Okay, we are 50% done with this problem. The last thing we need to figure out is RTH. Once we have RTH, we'll be done. Okay, so finding RTH. Okay, now here is where I caution people, because this is where I see the most mistakes. They try to do it all in one shot. They try to find RTH and VTH with the same original circuit, and then they get all mixed up in one circuit. It's a separate problem. I'm going to end up having a different circuit. I have to short out my voltage source. That is fundamentally different than this circuit. None of these values are applicable anymore. Once we short out that voltage source, all these numbers are meaningless. So redraw the circuit, please. I beg everyone to redraw this. Okay, 100 volts. $25 ohms, 25 ohms, 100 ohms, 100 ohms, terminals A and B, and we need to find the resistance between these 2 points. Okay, so step number 1, short out my voltage source. How does that change this circuit? Well, now my circuit looks like this. 25, 25, 100, and 100. Okay, now we need to find the resistance between A and B. Well, what do I have over here? Again, pretend to run current through this to help you with the series parallel stuff. Okay, if I follow the current, it divides here. It divides at this point. Does it divide going through this 25 ohm and this 25 ohm? No, the current doesn't divide at this point. Oh, so can we say that the current's the same through the 25 and the 25? Yeah, so they must be in series. Okay, so 25's in series with 25, just add them up. So once we go ahead, put the two 25s in series, we get 150, and we have that in parallel with these two hundreds. Okay, so now all of these are in parallel. Well, check this out. 100 in parallel with 100 gives us 50. 50 in parallel with 50 gives us 25. So this reduces to reduces to 25 ohms. So that's the resistance that we would find between points A and B when we short out the voltage source. So we have our Thevenin resistance now. Plug that in. Thevenin resistance, 25 ohms. Okay? Now we have two circuits that behave identically to each other, but from the perspective of points A and B. And we still have 4 minutes left of class. What can I do for you guys? Song and dance? More talk of ham radio? Why didn't the parallel resistors become 0? I will answer your question with another question. Why would they become 0? Why would all of these resistances in parallel become 0? I don't have a short that's in parallel when we shorted the voltage source. So here's where I caution, do not skip steps. When we shorted the voltage source, was this short in parallel with any of our resistances? No. What resistor? Okay, if you believe that this short is in parallel with any of these resistors, tell me which resistor it is. What resistor is this short in parallel with? Is this short in parallel with this? Remember what it means to be in parallel. So this is why I always say, current's your friend in this case. Current is going to guide you through a lot of things. If I pretend to run current through this, look at where my current divides, look at where it sums. It divides up here. This defines one side of my parallelism. Look at where the current sums back together down here. This point defines the end of my parallelism. This short is in parallel with this resistance. This will turn into 0 ohms. This short will cause this resistor to effectively disappear, and what we will be left with is a short in its place of 0 ohms. So this short will cause this resistor to disappear. Now let's go back to over here. When I shorted out my voltage source, the short was here. What is this in parallel with? Run the current through it. Draw it by hand. Convince yourself of what's going on here. It's not good enough to just look at this and expect to understand what's going on. My parallelism is between this point and this point, where the current divides, where it comes back together. Do I have a short that's in parallel with anything? No. The short just connected this side of the resistor to this other resistor. So all it did was this short turned this 25 ohms in series with this 25 ohms. But the short is not in parallel with anything. If this short was in parallel with something, I would see current divide from this point and this point, or anywhere along this wire. And that's just not happening here. Okay, so if you are still having difficulty, any difficulty with recognizing these shorts and this parallelism and the series stuff, please set up some office hours with me. We can't let this hang up continue on for the rest of the class, and definitely not into 311. Okay, so please, if you're still having difficulty with it, no problem, but just set up office hours with me and let's talk it through, and let's spend some time getting that out of the way. Okay? Okay, so actually, I thought that was a good question, because as we get more advanced, these little nuanced details and all of the stuff we previously learned, it's like our minds only have capacity for this much stuff, and once we start growing that, the old stuff starts disappearing, right? So let's make sure we stay on top of that and not forget our basic rules, our basic fundamentals of all of this stuff, because eventually it needs to just kind of be there, and we need to be able to work with it. Kind of like binary, right? When you're learning how to convert between decimal and binary, at some point it needs to be second nature, and it shouldn't be something that you have to laboriously write out all of the steps to get there. It just needs to be something you're super comfortable with as a computer engineer. And kind of the same is true of these basic rules of Ohm's law, KVL, KCL, parallel, and series. That stuff just kind of needs to be second nature, okay? So definitely we have our exam coming up next week. So what I'm going to do, I want to change the lab. We have a lab on Thevenin and Norton equivalent circuits. There is another side of this puzzle, which is a different process called Norton equivalent circuits. I want to change that lab. And so we will start the lab next time. So I'm reserving today's lab time for any type of assistance and help with any type of exam preparation. Okay, I don't want to lose a lecture to exam review, but I think we can go ahead and do some exam review if people have questions during the lab time today. Okay, so let's go ahead. Let's call this good. It is 10:23 right now. We'll return in 10 minutes, so 10:33. I'm gonna do. I'm just gonna hang out and help out where I can. So there's no official lab to start today. Okay.